All right, good morning, guys. Welcome to our first online lesson. We'll see how this goes. You should have already downloaded these notes for yourself, and you're either filling them out on your computer or you're handwriting them with me. So you should already have a copy of this. If you don't, go ahead and get it from Google Classroom, and then you can follow along with me. So today we are starting a new unit on gas laws. It's going to take us about 3 weeks to get through this unit. We're going to start out by talking about the different properties of gases and their relationships to each other. So the first table you see here is the different properties we're going to talk about and the units you're going to see throughout this unit. So on the left, you'll see the first property is volume. We're going to represent that by capital V, and that's always going to be in milliliters or liters. Temperature is going to be capital T, and we'll measure that in Kelvin, which is K. That's a little different for us, so I'll talk about Kelvin a little later. Pressure is going to be capital P, and there's lots of units you'll see for pressure. So kPa is kilopascals, there's atmospheres, millimeters of mercury, torr, and psi. So we'll see lots of different units for pressure. And then our last property is number of moles, which we'll represent by a little n, and obviously we already know about moles. The unit is mol. I know y'all are so happy to see moles again. You love moles. So the first thing we're going to talk about is just the different relationships between these properties when we're talking about gases. So you'll see 4 pictures here. We're going to talk through the pictures and how the properties relate, and then we'll just write down some things about them. So the first relationship we're going to talk about is volume and pressure. So as you change one of these two, as you change volume, what happens to pressure, or as you change pressure, what happens to the volume? So if we look at this picture here on the left, what you're seeing is just a canister. These little dots are supposed to represent little gas particles. So this could be just air, could be hydrogen gas, argon, doesn't matter. So what's happening is your gases are always on the move. Particles are always moving. So you can see these particles are kind of floating around. Occasionally they'll hit the edges of the canister. Occasionally they'll run into each other, but really they're just kind of floating around. What happens in our next picture is I am decreasing the volume. So as I push down this lid, you can see I have a smaller volume. And what's going to happen then is as you compress the volume around it, what's going to happen is you're going to have these particles, more of them are going to be colliding with the edges and with each other. So as you get more of these collisions, they're all knocking against each other, they're knocking against the walls because they have less space. So because they have less space and they're knocking into each other and the walls more, they have an increased pressure. So if we put that into words, as my volume decreases, like in the picture, my pressure is going to increase. The reason for that is when you have less space, you have more of these particles, they don't have as much room, so they're going to start running into each other, which is going to create more pressure. So the opposite is true also. So as our volume increases, if we go from right to left, so I pull this little plunger up to go from right to left, you can see that now my particles have more space, they're social distancing, right? And so now that they have more space, the pressure decreases. There is less pressure because there are less particle collisions happening. So when we look at that relationship, as volume increases, pressure does the opposite, right? So because they are opposite of each other, volume and pressure then we call inversely proportional. As one increases, the other decreases. That's called an inversely proportional relationship. So pressure and volume are inversely proportional. Okay, our second relationship we're going to look at is volume and temperature. So as you change your volume, what happens to your temperature and vice versa. So if we look at our little picture, again, the little dots are just my little gas particles. Could be hydrogen, could be nitrogen gas, doesn't really matter, argon. So what's happening here is I am applying a heat. So over here my little flame is smaller, right? So this should be a lower heat. As you crank up that heat, you start to increase the temperature. What you can see here is that as you increase the temperature, I'm also increasing my volume. So I can see I've got a bigger volume over here than I do over here. So when you heat up a gas, it tends to expand. It needs more space. So to put that into words, as your temperature increases, like we go from left to right, temperature increases, your volume also increases. The reason for that is as you're increasing the temperature, you're increasing the amount of energy that these little particles have. So they're moving faster and faster, and they need more space. So they expand to get more space. So the opposite is also true. As you decrease the temperature, your volume will also decrease because they have less energy, so they start to move a little slower, and they don't need as much space. So when we look at the relationship there, because when you increase one, the other increases, and when you decrease, for example, temperature, the volume also decreases, we call that a directly proportional relationship. As you increase one, the other increases as well. And the opposite is true. The third relationship we are going to look at is temperature versus pressure. So as we change temperature, what happens to the pressure in our system? And it's kind of hard to tell in my picture because I didn't get to print it in fancy colors, but online you saw it in color. So if you look, the one on the left is supposed to represent a low temperature. It had like a cool blue color. And the one on the right is supposed to be a higher temperature. It was in red, but you can't tell that here really. So what it's showing is that at a low temperature, my little guys are happy. They're kind of moving around nice and slow. They're not in a rush. It's like me during this COVID right now. It's not really in a rush to go anywhere or do anything. Okay, but as you increase the temperature, what's going to happen is you increase the energy. So if I'm increasing the energy, these guys start to move around a lot faster. And when they move around a lot faster, that means they're going to run into each other a lot faster. They start to get stressed. This is what I look like when I have to go to H-E-B during this COVID. I get super stressed, right? So people are all knocking into each other. I mean, they shouldn't be, but anyway, for the example, they're all knocking into the walls, they're knocking into each other, and so the pressure then increases. So as your temperature increases, your pressure also increases. The reason for that is an increased temperature increases the energy. Particles are moving faster and more chaotically. They're running into each other more, which is going to give you a higher pressure. The same is also true. So if you kind of turn that temperature back down, you decrease your temperature, your pressure will also decrease. Because less energy means particles move slower and less particles are running into each other, colliding. So in this case, again, I see that as I increase temperature, I'm also increasing pressure. So if they're both going in the same direction, that is called directly proportional. As you increase one, you increase the other. The last relationship we're going to talk about is volume in moles, because y'all love moles, so we're going to talk about moles again. But really what I mean by moles is the amount of gas. So how much gas is there? We just tend to talk about the amount in moles. So we use balloons as an example. So if I have a little tiny balloon, right, and I start to blow air into that balloon to make it bigger and bigger, what's happening is I'm adding more moles of gas. I'm adding more gas into the balloon, right? So in my case, when I'm airing it up, I'm adding more carbon dioxide into the system. So as you are adding more moles of gas, whatever that gas is, your volume increases, your balloon gets bigger, right? So as your number of moles increase, I'm adding more air into the balloon, my volume also increases. I think that's pretty intuitive. The opposite is also true. So when y'all, during that one experiment we did with the balloons, and y'all drove me crazy making the little dolphin sounds when you let the air out, right? So when you're doing that, when you're letting the air out and it makes that horrible squeaking sound, you're decreasing the number of moles because you're releasing all of this carbon dioxide from the balloon. When you do that, your little balloon gets all shriveled up and sad, so the volume decreases when the number of moles decreases. So again, if one increases, the other also increases, so that's called a directly proportional relationship. And I started out by highlighting all of these and then I stopped, but y'all know I'm a freak for highlighting, so I'm gonna go back and fix that real quick. So that's the basics of the properties we're going to look at and how they're related. Now, with each of these relationships, guess what? There's math that goes with it that helps us calculate these types of things. So I know y'all are super hyped about that. So for each one of these different relationships, we're going to talk about a gas law that corresponds to it and how we can use that to calculate things like pressure and volume and temperature, all that fun stuff. So that being said, we're going to move on to the second page. Gas laws and calculations, because I know y'all missed calculations over this break, yay. So we're going to talk about 5 gas laws altogether, but today we're just going to talk about 2. Next week we'll talk about 2 more. The third week we'll talk about the last one. So we're going to really split them up. The first one we are going to talk about is called Boyle's Law. So Boyle is some dude. They came up with this law. So Boyle's law shows the relationship between pressure and volume. So if we go back to the first page, we talked about the pressure and volume relationship, right? Up here, that was the first one we talked about. So Boyle's law used math to describe this relationship. So we said that volume and pressure are inverse. Boyle's law shows the inverse relationship between pressure and volume. So when one increases, the other decreases. The way you can represent that mathematically is with this equation. P1V1 equals P2V2. P1 over here on the left, that's your initial pressure, what you start with. V1 is your initial volume. And then after you apply a change, P2 is your final pressure, V2 is your final volume. And we'll use all those units in the very first table to kind of help us figure out, well, what's the pressure, what's the volume, and all that. So we're going to do a couple practice problems here. The first one says, a warning signal horn holds 2 liters of air at 1 atmosphere that is compressed into the 0.45 liter canister. If its temperature remains constant, what is the pressure of the compressed air? So that's a lot of words, right? Let's break it down. Let's see what it says. So it says a warning signal horn holds 2 liters of air. Liter means volume, right? At 1 atmosphere. So you'll get used to this, but if you don't know, you're like, well, what the heck is atmosphere? Go look at your little chart. Atmosphere relates to pressure. So 1 atmosphere is a pressure that is compressed into a 0.45 liter canister, so that's another volume. If its temperature remains constant, so that means we're not dealing with temperature at all here. We're not changing temperature. What is the pressure of the compressed air? So we want to know what's the final pressure. So if you see that it's talking about volume and pressure, you know you're going to use Boyle's law. So we're going to use this equation here. So just like always, my first tip is write down what you're given first and list it with the right variable. Okay, so it says that I'm holding 2 liters of air. Liters is my volume, so this is my V1. That's my initial volume, is 2 liters. At 1 atmosphere. So atmosphere we said is pressure, so this is my original pressure, 1 atmosphere. Okay, then it says we're going to compress that, so we're going to squeeze it into a 0.45 liter canister. So that is my V2. I'm going to change it to 0.45 liters. And we want to know what's the pressure. What's the pressure after we compress it? So we want to know, okay, what is P2 then? So we have everything we need to know. Now we can plug it into our equation, which is going to be this guy, P1V1 equals P2V2. So let's just plug in values. So our P1 here was 1 atmosphere. V1 is 2 liters. We set that equal to P2, which we don't know, so I'm just going to keep that as P2, times our second volume, which is 0.45 liters. From here, it's just algebra, guys. You can do this for sure. So we need to isolate P2 to figure out what the number is for P2. So that means I'm going to have to get rid of this 0.45. So I'm going to divide by 0.45 liters. That gets rid of it over here. Divide by 0.45 liters. I'm just going to rewrite that for y'all. So that means I've isolated my P2. So I've got 1 atmosphere times 2 liters on the left, divided by 0.45 liters is equal to P2. Then it's just about crunching numbers. Where is my calculator? Dang. Okay, well, I already have this calculated, so I don't have to show y'all, but all you're going to do is 1 atmosphere times 2 liters divided by 0.45 liters, and what you should get is that P2 is equal to 4.4. Okay, the units here. So we're talking in pressure. My original pressure was in atmosphere, so I know this has to also be an atmosphere. Another way you can tell that is that your other unit should cancel. So I had a liter on top here, one on bottom here. So all I had left was my atmosphere. That's my unit. The rounding is not like that big of a deal to me, y'all, right now. Just give it a decimal or 2. Okay, so we're going to do one more using Boyle's law, and then we'll move on to another law. So number 2 says bacteria produces methane gas in sewage treatment plants. Gross. This gas can be burned or captured. If a culture produces 75 milliliters of methane gas at 700 millimeters of mercury, what volume would be produced at 770 millimeters of mercury? Bleh, that's a lot of words, so let's break it down. Let's go find our info. Okay, so it says blah, blah, blah. If a culture produces 75 milliliters, that's a volume. I got that. So that's going to be my V1 is 75 milliliters. Okay, it says at 700 millimeters of mercury. That's a crazy unit, but if you go back and you're like, well, what the heck is that unit, Miss K? I don't know what you're talking about. Okay, that falls under pressure. So that's a unit of pressure. Pressure is measured in all kinds of units. So I know that's my pressure. That's my P1. Is 700 millimeters mercury. It says what volume would be produced. So that's my X here. That's what I'm solving for. V2 is, I don't know, at this new pressure, 770 millimeters of mercury. So I see I'm working with pressures and volumes here. I know that means I'm going to use Boyle's law, so I'm just going to plug it in. So P1 V1 equals P2 V2, then plug everything in. So my P1 here is 700 millimeters mercury. My V1 is 75 milliliters. Set that equal to my P2, 770 millimeters mercury, times my V2 is my unknown, so that's what we're solving for. So again, from here, it's really just algebra. So I need to isolate my V2. To do that, I got to get rid of 770. So to move it to the other side, I'm going to go ahead and divide by 770 millimeters mercury to cancel those two out. 770 millimeters of mercury. And then we just solve. So I'm not going to rewrite it this time. So we've got V2 over here. All you have to do in your calculator is 700 times 75 divided by 770. You don't need a fancy calculator for this. You can use your phone. It's not a big deal. So you should get about 68.2. We're talking volume here, so it's milliliters. You can also tell because these guys cancel. Millimeters is the only thing left. You can also stop here and check to make sure that your answer is reasonable. We talked about how it's an inverse relationship between pressure and volume, right? So if I look here from pressure 1 to pressure 2, I had increased my pressure. So if I increase my pressure, that means I'm doing the opposite to my volume, right? Because as my pressure increases, volume decreases. So I should expect, if my pressure increased, that my volume should decrease. And it does. It goes down from 75 to 68. So you can kind of check your answer that way too, based on what you know about the relationship. Okay, so if you have questions on these type of questions, please pop in during office hours or send me a text on Remind. I'm happy to help you guys. We are going to move on to the second law now. So that was Boyle's law, and now we're going to talk about old Charles's law. Good old Charles. So Charles's law talks about volume and temperature. volume and temperature. So if we look at the front, we talked about a relationship with volume and temperature. This one, we said as you increase the temperature, you also increase the volume, meaning that they are directly proportional, right? So Charles's law shows the direct relationship between volume and temperature because gases tend to expand when they're heated. So little notes here. I said earlier in the little chart up here that we're not measuring temperature in Celsius or Fahrenheit, we're measuring it in Kelvin. So that's something kind of new, but sometimes the question will give you the temperature in Celsius and you're gonna have to convert it. So your temperature has to be in Kelvin. The way you convert from Celsius to Kelvin, all you do is take whatever the number is, say it's 25 degrees Celsius, add 273 to it, and that gets your number in Kelvin. So just watch out for that, use that to make those conversions. Otherwise, it's just more math. So it's a direct relationship here. So when you turn that into a mathematical equation, this is what it looks like. V1 over T1 equals V2 over T2. So my initial volume over my initial temperature, you set that equal to your final volume and your final temperature, and you solve. But really, it's the same idea. So same type of questions, it's just different variables. So if we look at the first one, it says a balloon is filled with 3 liters of helium at 330 Kelvin and 1 atmosphere. The balloon is placed in an oven where the temperature reaches 340 Kelvin. What is the new volume of the balloon? Okay, so let's go break this down. So if I look at it, this 3 liters, that's obviously a volume, right? So I'm going to record that as my initial volume is 3 liters. Okay, it says at 330 Kelvin, that is my initial temperature. So T1 is 330 Kelvin. At 1 atmosphere. Okay, atmosphere is a pressure number. This is just there to throw you off. If it is asking you about volume and temperature, you don't see pressure anywhere in this equation. So you don't need this 1 atmosphere. So this you do not need. It's just to throw you off. Okay, so we are going to skip that because we're just talking about volume and pressure here. Volume and temperature here. So we don't need pressure. Okay, it says the balloon is then placed in an oven where the temperature reaches 340 K. So now our temperature has increased to 340 K. That's my T2. He says, okay, what's the new volume of my balloon now that I put it in the oven? So V2 is what? Now we just plug it in. So my new equation here is V1 over T1 equals V2 over T2. Just plug in numbers. So my V1 here was 3 liters over T1 is 330 Kelvin equals V2, I don't know. And my T2 was 340 Kelvin. So same thing here, we're just going to rearrange to isolate V2. So in order to do that here, I'm going to multiply both sides by 340K, right, to get that on the other side. So if I multiply by 340K on this side, that cancels them out. I multiply by 340K over here. I'm just going to rewrite that up here for y'all. So your new equation then is 340 Kelvin times 3 liters divided by 330 Kelvin is going to be equal to your V2. So all we have to do now is do 340 times 3 divided by 330, which should get you about 3.1 liters. So my V2 then here is 3.1 liters. Liters is the correct unit because I'm talking in volumes, and liters is what I used before. My Kelvins had canceled. So your final volume is 3.1 liters. And you can check this again. So we said that there is a direct relationship between volume and temperature, right? So as you increase one, you increase the other. So if we look from T1 to T2, we increased from 330 to 340. So if we increase the temperature, our volume should also increase, and it does. So we increased from 3 to 3.1, so it makes sense. Okay, last problem. So last problem says the volume of a sample of argon is 8.5 milliliters at 15 degrees C. What will its temperature be at 8.20 milliliters? Okay, so let's pick out info from this. It says my volume is 8.5 milliliters. That's my V1. All right. My temperature, it says, is 15 degrees C. Red flag, red flag. It can't be in degrees C. So T1 right now is 15 degrees C. Okay, but that's just because we're trying to make your life difficult, because it can't be in degrees C when we're talking about gases. I said that up here, right? Has to be in Kelvin. So to convert from Celsius to Kelvin, all we're going to do is add 273. So very important step. So to convert this, we're just going to add 273, which is going to get you, I solved this earlier, 288 Kelvin. So be very careful. Don't forget this step. It cannot be in Celsius. It must be in Kelvin. Okay, then it says, what will its temperature be? So T2 is what we're looking for. If we change the volume to 8.20 milliliters. So V2 then is 8.20 milliliters. Again, then we just plug it in. So V1 over T1 equals V2 over T2. Plug it in and solve. V1 is 8.5 milliliters. T1, remember to use the Kelvin number, is 288 Kelvin. Our V2 is 8.20 milliliters. And our T2, we don't know. That's our unknown. From here, it's just algebra. Now, some of you get all like, oh my God, with algebra, especially when this guy's on the bottom, right? So there's a couple extra steps here to solve, but just be really careful with your algebra and you'll be just fine. So we know that T2 can't be on the bottom to solve for it, right? So we have to get T2 up on top to solve for it. So the way I start with it first, there's lots of different ways you can do this, but I'm going to get T2 on the other side first. So I'm going to multiply by T2 to cancel it here, to put him over here. And I really didn't give myself enough room for this, but I'm going to rewrite it up here and try to write it small. So now I've got T2 times 8.5 milliliters over 288K equals 8.20 milliliters. Okay, then I have to get rid of these guys, right, to isolate T2. So I am going to multiply by the inverse on the other side. So T2 then is going to be equal to this guy, 8.20 milliliters, times the opposite, because I would multiply 288 to get it to the other side. So he's going to be on top over here. And you'd have to divide the 8.5 to get it on the other side. And I know I could explain that better, but I really kind of ran out of room. But if you have more questions about algebra, office hours, come talk to me. So we're just going to do 8.2 times 288 divided by 8.5, which should get you a T2 of 278 Kelvin, not Celsius. And again, you can check yourself. Temperature and volume are directly proportional, so let's look at our volume. From V1 to V2, we decreased volume. So if we decrease the volume, that means our temperature should also decrease. So we started at 288, we did decrease to 278, so that makes a lot of sense. Okay, so that's all we're doing for this week. You have a couple assignments that are all on your to-do list. The problems I'm going to give you look just like these, but if you need help, please come talk to me during office hours, email me, send me a reminder. I'm here to help you. So thank you guys for watching, and we'll talk again soon.